Okay, so welcome to part 2 of the chain rule. If you haven't watched part 1, you should obviously do that before watching this one. In that part, we learnt about the chain rule in its original form, and then we used it to differentiate this function over here. After actually working through the derivative, we remarked that it was way too much work, and I promised that I'd give you an easier way to actually find the derivative whenever you needed to use a chain rule. I hope to deliver on that promise in the rest of this lesson. In a sense, we're taking the input from one function and putting it into another function. So it's almost like you have a function inside another function. Ever since I realized this, I've basically always thought of the chain rule almost like the mathematical version of a Matryoshka doll or a Russian doll. Now, if you've never actually seen a set of Russian dolls before, you might have no idea what I'm talking about. And even if you have seen a set of Russian dolls, you might still have no idea what I'm talking about. But I'm going to make it very clear for you, hopefully. The thing about a Russian doll is, you can always take the top doll and lift it off to reveal another doll. And if there's another doll inside, you can even lift that one up to reveal yet another doll. Now the way these work is, every time you lift a doll, you reveal another doll below it. And if you lift the next doll, you might reveal another doll below it yet again. This will continue until you get to the last doll in the set. Now this behavior is the exact same behavior that you actually see in the chain rule, and as soon as you see this, the chain rule becomes a lot easier to compute. To show you this, I'm actually going to write out the chain rule again, but this time I'm going to use my own box notation. So each shape here actually represents a function, and over here we actually have three shapes embedded inside of each other. Now in order to differentiate a function that's equivalent to a bunch of functions embedded inside of each other, we just have to unpack the inner functions just like this. Now the checky shape over here just indicates that this function's been differentiated. And when we write it in this form over here, we're saying differentiate the outer function in terms of the inner function. So I hope you see the analogy to the Russian dolls. This one kind of looks like this small doll, this looks like the next doll, and this term over here looks like the bigger doll. If you don't see the analogy to the Russian doll yet, you definitely will when I show you an example. Now just to test out how useful this method is over here, I'm going to give you a much harder example than the one we had over here, and we're going to use this method to solve it. Now this time the function I'm asking you to differentiate is actually a lot more complicated. So we're always going to start by drawing boxes around all the things that we can differentiate. So on the left I just have a normal function, but on the right I have a box inside of another box which is inside of yet another box. So now I'll just go ahead and show you how to apply this Russian doll rule of mine. So to use this rule, the first step is going to be to cover this inner part and just differentiate what's left. Here we have something to the power of 5, and if we differentiate it, we just get 5 times that thing to the power of 4. Now throughout this process we didn't actually look inside this function, so this part over here will not change. Just like if we move the first babushka doll, the second and third babushka doll won't change either. Now I'm speaking figuratively. Since we've removed the first doll, it's time to have a look at the second doll. So I want you to ignore this part on the outside, we've already used it. And now we want to differentiate this inner function over here. And now to actually do this, we cover up this term over here. And now we're differentiating 3 times something to the power of 3 minus 7, which would just become 9 times something to the power of 2, and then the 7 would just go away. Now again, because we had this term covered up, we don't actually change it at all, so we just copy it over here. And now finally, we've actually used up these outer two layers, and we've only got the innermost layer left, and its derivative is just 1, so we're just going to write that over here. And of course, since this is all equal to the derivative of this side on the left, then this whole thing is just equal to h-x. And if you're anything like me, I'm sure you found this a lot easier than the last example. However, you might actually have one objection. How do I know that this and this are actually the same rule? Like, where did this actually come from? Coming up with it yourself isn't actually so complicated at all, as long as you're willing to make up your own notations like I did here. To show you where it comes from, I'm going to copy out the equation for the chain rule. Now to get this formula over here, we assume that h of x would just be a function inside of another function. So I'm going to represent this as a triangle inside of a circle. Now ordinarily, this h of x is actually the same thing as this g of f of x, as we said before. Now this was actually the inspiration right here. we have a triangle inside of a circle, or an f of x inside of the g. So therefore my triangle represents f, and my circle represents g. Now if the triangle represents f, then df on dx is just the same thing as the Chequy triangle. And now I'll also replace these g's and f's with their corresponding shapes. So now this term over here is telling us that we want to differentiate the circle within the triangle in terms of the triangle. So then at this point it's just a matter of coming up with your own notation for this sort of thing. So instead of writing this whole thing over here, I just draw the circle and only put the checkies on the outermost function. Now all I've really done here is I've rewritten the chain rule in terms of my own notation. But as you hopefully saw up here, this notation is actually really useful to help you solve problems. And hopefully this teaches you an important story about how you should do maths. Of course, this isn't the only way to do the chain rule. This is just something I made up to help me understand this stuff better. So anytime you are given some kind of problem to solve, it's always a good idea to prod it and look at it in different ways so that maybe you can come up with something that can help you solve the problem in an easier way. And now with this, we've actually completed our examples. And now I'd like to summarize this lesson. This lesson was about differentiating functions that are nested inside of other functions, as you can see over here. We found that anytime you have a composite function like this, any change in the outermost function can be attributed to changes in the two innermost functions. We found out that the slope of the outer function is the same thing as the product of the slopes of the inner functions. Then after this, we actually use this to write down the derivative and then do a little bit of algebra to get to this form of the chain rule. We found that using the chain rule was a little bit annoying, but it was doable. But then we introduced this Russian doll method that was actually a fair bit easier to use. No matter which form of the chain rule you use, it's always going to come down to multiplying a few contributions by each other. And now with that, we've actually completed our discussion on the chain rule.